There may be some of you in the audience that may not have heard of Nassim's work in the Resonance Project. Anybody? Oh, wow. Okay, so we're good. All right, but I got to do the man justice. He's been doing this for a long time, and for those of you who might not have heard his background, Nassim was born in Geneva, Switzerland back in 1962, and as early as 9 years old, he was already discovering universal dynamics of matter and energy, which led him on a journey towards pioneering a new approach to quantum gravity and continual developments in unified field theory. He actually grew up in Eastern Canada with an innate reverence for the design of nature and a determination to discover the basic building blocks of creation. Nassim's dedicated most of his time to his independent investigation of physics, geometry, chemistry, biology, consciousness, archaeology, and various world religions. He's clearly a man after my own heart here. His dedication to scientific exploration, combined with his keen observation of the behavior of nature, led him to a specific geometric pattern, which is the core of his approach and new perspective in unified field theory. He's fluent in both French and English, and he's been delivering lectures and seminars on unification theory for over 20 years worldwide. In 2003, he founded the Resonance Project Foundation, and as its director of research, leads teams of physicists, electrical engineers, mathematicians, and other scientists to explore the frontier of unification principles and their implications. Nassim's lifelong vision of applied unified physics to create positive change in the world today is reflected in the mission of the Resonance Project Foundation, and he shares the developments of his research through the scientific publications and educational offerings through the Resonance Academy. So let's give a warm Toronto welcome to the one and only Nassim Haramein, ladies and gentlemen.
Hi, everybody. Hi. Thank you. Thank you. Thank you so much. It's great to be here. Wow, it's my first talk in Toronto. Hopefully not. So I'm excited to share this presentation with you. I've been kind of going around, you know, I was in my cave in my lab, kind of cooped up for almost 3 years, and just started to tour again. I was in Paris a few weeks ago, and Belgium, and Montreal yesterday, and you know, it's remarkable the response I'm getting, but as well, you know, where are people at, and how much, I mean, engineers, scientists from all flux of life are like coming to this, and it's amazing the momentum behind it. And why is there such a momentum? I mean, the Connected Universe movie, I believe, got the best crowdfunding result in history of Indiegogo. Remarkable. We needed to raise funds to improve some of the, to put and improve some of the animations in the movie. And I mean, this movie is going to be incredible. And it's due to your generosity. So thank you so much, everybody, for participating and being involved. And it's exciting to see. I want to present to you today this view of the connected universe that's emerging in science, because it says a lot. It says tomes about who we are, the universe we live in, and how we interact with it. And most people think of this kind of stuff as stuff that is kind of woo-woo, and it's kind of nice philosophical idea that we're all one and all this stuff. But actually, the physics are now showing us that it's really actually the way things work. And that you can take these concepts, write the physics, and get very accurate, very fundamental understandings of the forces of nature and the material world in it. And it's exciting as well, because it not only unifies the forces of physics, but it unifies the concepts that are typically polarized between spirituality and science, which, all of a sudden comes together where you realize that the material world is actually an expression of what we call the spiritual world, or that what we call spirituality is actually the physics we haven't quite understood yet. And so this is really, really critical because it has the potential to launch our society into a whole new way of interacting with nature. So you can think of the universe as the standard model and the mainstream scientific community typically think of as this random entropic system that always moves towards disorder, and that where things happens by chance, and literally quantum theory is written in such a way that it is a statistical analysis of the probabilities. Or you can actually, from observation, come to different opinion about the universe. Because the mere fact that we observe the biosphere all around us and the complexity of even just our being in the biosphere kind of points to a universe completely different than that one. Because this complexity and this very advanced, systems that we see in the bioorganisms and in the biosphere systems does not point to a random, entropic behavior of nature. It actually points to something that's highly organized, highly communicative, like that is talking very much so, and that is highly coherent, and that strive for coherency, for complexity, that moves towards complexity and advanced systems. And so how we reconcile these two views? Well, let's assume that we think of the universe a little differently. There's a reason why the mainstream scientific community is insisting that the universe is random, philosophically, and that there is no organizing systems, is because they have been for a very long time trying to get away from religions and dogma, and so the idea that when you start talking about there's organization in the universe and so on, the tendency is to think, oh my God, he's gonna start talking about God organizing the world or religions, and that's what science wanted to get away from. And in doing so, they've created their own dogma. And that is not necessarily an appropriate scientific approach. That is, as you discover that there is incredible complexity and that mathematically the concept that the universe is random doesn't actually work out, you should start looking for alternatives. So there's an alternative to going to some religious beliefs, but as well understanding that the universe may be much more advanced in its capacity to relate to itself than previously believed. That it's not just a big boom that happened and somehow miraculously we got here, right? And we'll talk about that. It would be really miraculous, right? So a unified view of the universe. If the universe is unified, what does it look like? And how? I mean, this is what I wanted to know. It's like when I was young and I was in nature, and I'm a sport jock. I'm like crazy on sports. I used to be a ski coach and a ski instructor for many, many years. I'm a climber. I'm a backcountry skier. I'm a scuba diver. I surf big waves in Hawaii all winter long. I'm into it, right? And I'm in nature, and when I look at nature, I look at this incredible thing that's happening, this incredible miracle that's happening, and to me, it seemed unified, you know? Like the bee somehow knows that it's got to go to the flower, and it knows how to deal with that flower so that there's more flowers that happens, and you know, and the whole system and everything is just tuned perfectly so that all this stuff happen. And literally this is called the fine-tuning problem in physics, okay? It's funny because it's called a fine-tuning problem, but it's not a fine-tuning problem, meaning it's like a big problem, right? Because the fine-tuning problem is that, like, if the electromagnetic field in the universe was just a little different and the gravity was a little bit different, you know, like anything, anywhere, in any shape, a little bit different, none of this would happen. Like it would all just go, you know, like it just wouldn't happen. And so it's kind of puzzling, like, okay, why is it like actually tuned perfectly for this to be happening, right? And, you know, there's views where, which I think is kind of a like way to avoid the issue, saying, oh, well, there's infinite parallel universes and we just happen to be in the one that's tuned perfectly. All the rest are like a big mess. Okay. Well, either than that view, maybe there's another thing that, like, it's tuned perfectly because it actually knows what works and what doesn't work, right? Maybe it's actually talking to itself. Maybe there's feedback. Maybe, you know, the fact that we see feedback everywhere in nature is actually because it's an expression of what's happening at a much fundamental level in the material sciences, in the physics. Maybe there's feedbacks in the physics. Maybe there's something talking to something in physics, right? Maybe it actually knows what it's doing. And maybe the fact that consciousness somehow is present is not just some random events that's kind of like miraculously happened, but it's fundamental to the way things are. So, you know, I kind of got lost. I have a presentation to give. You know, we got to have tea one day and talk about this. But this division in our thinking, this idea that things are isolated, things, you know, that we can observe something over here and ignore the rest of the stuff as if that thing was separate from that thing over there, is present everywhere in our society. And, you know, even in our physics, we have that. Meaning the standard physics we have today have this big separation in it. Cosmological physics basically is dealt with Einstein field equation that describes the gravity at the levels of galaxy and stars and universes and, you know, quasars and planets and this stuff. And quantum theory, on the other hand, describes the subatomic particles, the atomic structure, even the molecular structure at the very fine level. And the two don't agree. They don't agree at all. Einstein field equation describes the universe as this space-time metric that is smooth and curving to produce gravity. Like Einstein described gravity as like if you put a ball, if you put a mass, right? So it's part of the equation, mass producing curvature. So if you put a mass on a structure like a trampoline and it curves that trampoline, another ball would appear to be attracted, right? And but he didn't say actually, and this is why we actually don't exactly know what gravity is. He didn't say what space-time exactly is. So, you know, that doesn't, all right? But it says it's smooth, right? The equation says it's very, very smooth. And if you look on the quantum side, when we look at particles and how we express the physics of particles, we're finding that at the quantum level, everything is quantized. It's very defined, linear functions that make boundary condition. And so it's granular, so it's not smooth at all. And so the two don't agree. And for, all of his life, Einstein, after writing Relativity, tried to find a way to solve unification, to bring gravity into quantum physics, and find a way to describe gravity in a way that would work for bounded states of quantas of quantum physics. And literally all his life he worked on it. Literally hours before his death, he was trying to solve this, right? And then something he said that was really important, he said, and I quoted that in my latest paper, he said, when we find the solution, most likely it's going to be really simple, it's going to be geometric and algebraic in nature, it'll be geometry. Because Einstein was strong on geometry, he's well known for having geometrized space-time, right? So the two don't agree. We have this split, but it's not just in physics that we have this split. There's many ways we can look at this split in our society. For instance, men and women. Men typically think in bounded linear states, right? Like finite function, right? Like they do one thing and then they do another thing. Women tend to think in more open, like infinity kind of thing. They can like have the baby on the hip, with the milk and, text at the same time, and with their toe they're doing the dishes, and it's like, no worries, right? Kind of separate way. And that division happens in many different ways in our society. So it's really fundamental in one way. It is similar to the division between spirituality and science. Like science tend to think in very bounded, linear way. Spirituality thinks in kind of infinities, kind of way. And so the two don't agree. But the thing is, and that kind of, when I used to go to physics conference some 25 years ago, and I would talk to physicists and give my presentation and kind of dodge tomatoes, I would always be surprised because some physicists, and that was the opinion of most physicists at the time, and it's just because they were told that as students, so they just repeated it. But their idea is like, well, it's okay to have two physics. There's no need to try to unify them. We just have physics for the big stuff and physics for the small stuff, and that's the way the universe works. And then I'd be like, but wait, that's hurting my brain, brah. Because like, the big stuff is made out of the little stuff. So how is it that where exactly does the universe change the equation? In between the big stuff and the little small stuff? Like, where is, that kind of doesn't work. And, usually the response I got after that was like, well, if Einstein didn't figure it out, dude, give it up, brah. Thing is that Einstein didn't have the mathematical tools or, necessarily the data that we have today about what we're finding out in the universe and what we're finding out at the quantum level. So, it would have been harder for him to put it together, a lot harder. And, and as well, Einstein never agreed with some of the fundamental principles of quantum theory, and so he was pushed aside very quickly after writing Relativity. So it was kind of difficult for him to get that. But today is a different it's a different world. And today we've drilled down into, galaxies and stellar objects and atoms. And as we drill down on both sides of these equations, we reach very interesting points. So when I was doing all this, I was like a heretic, living in a van by myself, isolated. And so I was thinking there must be a connecting point. Like, can I find a place where Einstein's equation kind of meets quantum theory? Like, is there something that connects the two? How, if I could find something, just one thing that I can find in both places, then that might be the link that I could, eventually find a unified view from. And I realized when I was studying black holes that Einstein predicts black holes, right? Meaning that Einstein general relativity equation for gravity predicts, a singularity, a point of infinite density in the middle of the black hole. Meaning that space-time is curving to infinity in that place. And I want to mention something really important, is that those equations are used every day by scientists, right, astrophysicists mostly, to describe orbitals or to describe masses of objects in the universe and so on, all the time. And every time they do, they actually describe that mass, they actually describe that object as a black hole. But they don't necessarily pay attention to that. Meaning that if they want to, describe the sun or, the moon or the planet orbiting around the sun, and they want to, calculate the orbits and all this stuff, they start by solving Einstein field equation. They start by solving the Schwarzschild solution, is the solution to Einstein that predicts black holes. They solve that for the sun, and they solve that for the Earth, and then they looked at the orbital relationship between the two. So they've made the sun into a black hole, and they made the Earth into a black hole, but only mathematically, right? And then they describe, they can calculate all the stuff that these objects are doing. But in some ways, not realizing that they've done this. That they've used an equation that says in the center of this gravitational field that you just described, there's a point of singularity, a point of infinite density, right? And because what we do in physics is we only look at the gravity where it's weak, not where it's very, very strong, right? Only where it's strong near black holes, where we say, well, that is a black hole we're observing. So not to confuse you, when I looked at this, I started to realize, well, wait a second. When they do this, they get infinity. And from quantum theory, I knew that when we drilled below the nucleon of an atom, when we went further and further and further, we reached what's called quantum field theory, where not only the particles are quantized, but the electromagnetic field is quantized. And there, the equation as well says there's an infinite amount of energy in every point in space. And I'm like, wait, I got two infinities. I've got two singularities. Maybe this is the connective tissue. Maybe this is where, the two come together. Maybe I can extrapolate the gravitational effect, the singularity of a black hole, out of the vacuum energy infinities at the quantum level, at the very fine level. And in both cases, the equations are renormalized, or there's a cutoff value that's used, so that it's not an infinity in the equation, but it's actually what's called the Planck length. So the two lead directly to the Planck length. And the Planck length is a little electromagnetic fluctuation of 10 to the minus 33 centimeters, so it's teeny, teeny, teeny. That's the wavelength of this oscillator. And it's present everywhere. But basically, this is the cutoff value that was given for the black hole and for quantum field theory. So I know I've lost a whole bunch of you out already. All I'm trying to tell you right now, we're going to drill into this and you'll understand it. It's not that complex. But all I'm trying to tell you is that this little entity, this 10 to the minus 33 thing, this little oscillator, okay, seems to be present in both theories, okay? And it might be the connected dot, literally, of the two. You see, if you were to start, instead of everything is disconnected and everything is independent from each other, to a theory where everything is connected, then you'd have to say, okay, well, what's connecting everything? You know, what is present everywhere that makes it possible for everything to be connected, right? How is it all connected? Because it doesn't appear to be connected in our daily life, other than in the laboratory where we see that particles seems to be entangled. So if you thought of all the things that could connect everything, eventually you would get to this. The only thing you can find everywhere is space, right? Because we have space between galaxies, we have space between planets, stars, all this stuff, there's space everywhere. And if you look at the atomic level, if you take the densest, molecule, like carbon, like diamond, if you grew one of the atoms in that molecule so it's an orange, the other orange would be like 2 football fields away. So there's a lot of space there too. And even the atom has 99.99999% space. I think I got a laser, yeah. And so space is everywhere. And I think this is really significant because you get these spiritual people all the time saying, well, it's so dense down here. And it's like, dude, it's 99.9999999% space. What do you mean? But we pay a lot of attention to the 0.0000001%, right? Because we think of that as our reality. Like, in fact, all you have is space that's wiggling a little bit, right? And we call that a reality, and we think, all we're touching here is a little solid space. Right? I think, actually, nothing has ever, that might be disconcerting for your partner, but nothing has ever touched anything. Literally, huh? Not even close. All you have is like electrostatic fields that are interacting with each other. It's like bouncing off each other, but it's not touching. And in fact, if you were trying to define the concept of touching, you'd have to have something, and you can't actually find anything. Nothing. Meaning the nucleus of an atom, which is like the heart of the atom, the mass of the atom, if you look in it, if you look at the proton, we call, for instance, the radius of the proton the charge radius of the proton, because all we can say is that in that region of space, there's more charge than in that region beside it. There is density charge in that region, we call that a particle. But it's not a billiard ball, hanging out, not. And even physicists are typically confused about that because they build huge things to like collide these billiard balls to get smaller billiard balls and then smaller billiard balls. But you see, your physical body is made out of those things. So when you think of yourself, do you actually think of your 99.9999999% space? Probably not. So it appeared to me very early that maybe it's the space that defines matter, not matter that defines the space. Maybe we should pay attention to the 99.99999% instead of the 0.00001%. Because I mean, if that space is actually something instead of nothing, maybe it's just the space dividing that makes it so that there's a little jiggle that we call matter in it. You guys see what I mean? Well, you might say, well, what do you mean the space is something instead of nothing? Well, you know, you typically think of the space between us as empty. You might think, okay, well, there's a little bit of air in it, like a little molecules of air, but generally it's empty. But is that true? No, it's only empty to your perception of the space. I mean, if I brought certain instruments in here to measure the electromagnetic radiation in this room, it would be far from being empty, right? This room is full of X-rays, radio waves, even gamma ray from galactic, you know, cosmic gamma rays. And I mean, like, there's all sorts of stuff going on in here. There's all the radio station with the radio waves and all this stuff. And the fact is that even if you just took a little radio box, you could just tune the little crystal, and all of a sudden you hear the announcer in there. Is the announcer in the box? No. Are you typically conscious that there is an announcer or there's music on the radio waves in the room right now without the little crystal tuned to it? No. But you could actually think of your brain and your nervous system exactly as this radio set tuned to a very specific channel that you call you, if there's information in the space, right? So of course, you're not necessarily, you know, I always say, like, looking for consciousness in the brain is like looking for the announcer in the box, just not in there. So if you were to, like, all of a sudden get that, because you see, you can pick up the radio waves with this little box. You can pick up the electromagnetic spectrum with this other little box. You can pick up all this stuff. But imagine if, I mean, you're not experiencing it directly every second of the day, but imagine that there is fluctuation of the electromagnetic field, that there's information riding on an electromagnetic wave that's way below, way smaller wavelength, way higher frequency, right, than anything we can pick up with all these cool boxes we've developed in the last 100 years, right? Just like before we had any idea that X-rays were there, we thought there was only the visible spectrum of the electromagnetic field. We had nothing to detect any wavelength other than that, other than our eyes. And then we figured it out, right? Mostly by errors. You know, somebody forgot a little uranium near, you know, photographic plates, and all of a sudden it's like, oh, wait, there's something going on. You guys following me? So this stuff is happening at a really small level of existence. How small? I know I can't do that. Okay. Well, you know, I'm not the only one that have talked about space that way. Actually, some of the greatest thinkers on our planet, some of the best scientists on our planet, made very, very profound statement about space. So I'm not like way out there in left field. Okay? Actually, I am, but I'm in good company. I like the left, you know, it's kind of nice. The right too, you know. It's all in balance. What's that? Yeah, I have company. And these guys were mostly ignored on that subject, you know. The world tends to take what they like and not necessarily what they don't understand. So, for instance, John Archibald Wheeler, a collaborator to Einstein, you know, really amazing guy. Probably the best physicist ever, I consider, for me. No point is more central than this, that empty space is not empty. It is the seat of some of the most violent physics. Actually, Wheeler theoretically got to the point where he kind of thought that the structure of space-time at the quantum level, at the very fine level, at the Planck size, is riddled with wormholes and black holes and a very small one, and it's like fluctuating like crazy, because that's what his equations were telling him. Those guys don't make statements like that if they have no physics to back it up. Just so you know, they're not just talking philosophically, and we'll see why they were able to make those statements. David Bohm, space is not empty, it's full. The universe is not separate from this cosmic sea of energy. Space is not empty, it's full. Of course it's full. We know it's full, even at the electromagnetic spectrum that we can measure, right? Einstein, physical objects are not in space, but these objects are spatially extended, saying that an object is not like something that's just sitting in the space, but actually an object is space extending itself, making itself visible, making itself something we experience. Okay, at certain frequency, it becomes an object. In this way, the concept empty space loses its meaning. So some of the greatest thinkers were very much so on the trail of figuring out what is that thing we call space. And is it something fundamental to creation? Well, I assure you that if it's 99.999999999% of everything we see, it's most likely important. Right? Okay. Well, when the reason why these people were able to make these statements is, as I was saying earlier, when we came up with quantum theory, did you all know that quantum theory emerged because of a light bulb? You didn't know that, right? Actually, Max Planck, considered the father of quantum theory, was commissioned by light bulb company to make a better light bulb. I mean, that's how it started. And as you know, of course, he looked at the element in the light bulb and he said, well, I've got to figure out, calculate what's the heat, what's the radiation coming off the element to try to improve it. And when he used the classical theory of the time to calculate that, the answer was an infinite amount of ultraviolet. It's called the ultraviolet catastrophe. And in laboratory, we don't measure an infinite amount of ultraviolet, so it was wrong, and people were trying to find solutions to that. And he tried to figure it out, and as he tried to figure it out, he figured out something. He found that if he added this little fudge factor in his equations, in the classical equations, he would get the right answer. So he calculated exactly what that fudge factor should be, and when he got it, right, he published it, but he published it saying, this is really kind of yucky, I don't like this physics really, because it was counterintuitive, because the physics were saying when you're boiling water, it's not boiling smoothly to a temperature, it's going through these little quantas of energy that were that value that he had to keep putting in. And that became the Planck's constant. Because it was eventually found that actually that's kind of fundamental to how the universe does things at the quantum level, that an electron in an electron cloud will, you keep putting energy, will only jump to the next level when it reaches that Planck energy level, and it will just go in quantas. It won't smoothly go from one shell to the other. It will only jump to those very specific integers. And this is why it was contrary to what Einstein was saying, because Einstein was saying space-time is smooth. Even at that level, it should be smooth. It ain't smooth. It's integers. And so that was all cool, that was all good, but then that meant, and Einstein used that to write his paper on the photoelectric effect, which got him the Nobel Prize. They had to give him a PhD first, and then they had, and he, I think he coined the word photon, and the little particle of light. But that was all good, except that when they extrapolated the theory to the electromagnetic field as a whole, something didn't work. That is, the equation said that the electromagnetic field was composed of these little quantas everywhere, but these quantas were going to infinity, meaning there was an infinite amount of quantas, meaning they couldn't find the end of the electromagnetic field in the structure of space. When they went to the structure of space-time at the quantum level, what Einstein had described at the cosmological level, the equation was saying there was infinities in every point in space. Every point in space was a black hole. But they didn't think of it that way because black hole hadn't been found yet. Einstein didn't have that luxury. He thought actually his equation that predicted black hole needed to be ignored. That part needed to be ignored, that, these things probably don't exist. But now we know they exist because we see them in the universe. So quantum field theory predicted an infinite amount of energy, but that's kind of uncomfortable. I guarantee you, it made a lot of people uncomfortable at the time. Because, infinities in physics are kind of like not so accepted. I mean, an infinitely small number is easy. You just ignore it. An infinitely small quantity, you just say, it's infinitely small. It doesn't matter. Right? But when the equation tells you it's an infinitely large quantity, especially of energy, it's like, oh, what do we do with that? Right? And so physicists said, well, let's try to figure out, actually, maybe, there's a cutoff to the smallest thing that your universe can do in electromagnetic fields, meaning since they had the Planck length, the Planck constant, they could extrapolate the length, like what is the length of the Planck constant? What is the wavelength of the smallest thing the universe could do, the the minimum quanta, the minimum photon. And so they use the Planck length. They say, okay, we're going to cut it off there at 10 to the minus 33 centimeters. Now, do I think that the universe doesn't do anything smaller than that? Absolutely not. I think there's sub-Planckian scales. But I think that the Planck scale is a very important pixel size for our universe. And you'll see my equation proves that. It is critical to the way our universe functions. And it has to do as a harmonic relationship to the size of our universe. That is, it's the size of the Planck length because the universe is the size it is. It's a pixel size that makes up our universe. So how small is the Planck length? I forget, I can't click this because it won't go. Okay, so, I'm sorry, things have gone awry. Okay, so let's start with the Vatican Dome for like something that we can relate to. Anybody here been to the Vatican? Yeah, it's a big dome, right? About 42 meters. Okay, when you're in the middle, you're like a little thing, you know, in this huge dome. And because the staff at the Resonance Project are extremely dedicated to my presentations, I asked Susan to climb up there. She's amazing, huh? And Susan, like most of us, is made out of approximately 100 trillion cells. I'm trying to give you an idea of scale. Okay? 100 trillion cells. That's what you're made of. Cells are, you know, we think of cells as pretty big because we see them in the microscope. But they're pretty small because there's 100 trillion of them. It's a non-trivial event. And, you know, there's 100 trillion of them, and, you know, you tend to say, oh, I'm one person. Well, there's 100 trillion entities that disagree with that whole statement. Okay? And so 100 trillion cells are hanging out, making you, dividing at millions of division per minute, okay, with like billions of chemical change every second to make the whole thing work, like clockwork, for like years after years after years after years. This is what you're actually made of. And we have an idea that this is all happening randomly. Okay? I don't think so. In fact, in the paper that we just delivered at the science conference in Barcelona, we calculated with the help of William Brown and Dr. Waldbaker the probability for even just the simple, you know, single cell system, like really simple, you know, receptor sites to come together to produce like the most fundamental principle of life. And like, what were the chance in like some kind of Big Bang random thing universe, you know, Dr. Rauscher called it the dead horse universe, you know, it's kind of dying kind of thing. What the probabilities are, and the probabilities are that even just for that first little spark of life to happen, you would need 10 to the 8,896, you know, wrong before you got it right. Right? Okay, just to give you an idea of that number, which is completely irrational in any time period, like 13.7 billion years since the Big Bang just doesn't do it, like you're needing billions and billions of years more. The radius of our universe is a big universe. In centimeters, centimeters are small, is about 10 to the 28 centimeters. Okay? That's the number of centimeters that makes up the radius of our universe. So that gives you an idea. 10 to the 8,896 probabilities is a lot. Okay? And so you're made out of those 100 trillion cells, miraculously, randomly adjacent to each other, you know, happy to collaborate. And each one of them is made out of 100 trillion atoms. So like, are you starting to get a sense of scale? Okay, you're made of 100 trillion cell. Each one is made of 100 trillion atoms, so the atom is already extremely small, right? Okay, now if in the middle of that dome was the atom, then in the middle of the dome, we would find the proton, and it would be approximately the size of a head of a pin. So that would be the proton, the teeny head of a pin. So the proton is really small. Okay, this is all to tell you how small the proton is and how much of a miracle it is that you're here, sitting, listening to me, like, you know, just in the passing. And so now that we have an idea how small the proton is, if I were to take a Planck, which is 10 to the minus 33 centimeters of Planck length, and make it the radius or the diameter of a grain of sand, okay? A grain of sand is already pretty small. Like on the Earth, it's really teeny. You can't see it, right? Okay? And if I was to say, okay, well, here's the Earth beside the sun. The sun, you see it's flying by here? It's really teeny. This really teeny thing, that's the Earth. So now the grain of sand on the Earth, right, and the Earth beside the sun, then if the grain of sand was a Planck, then the proton would be approximately the distance between Alpha Centauri and the sun, which is 40 trillion kilometers. So when people say, but I'm not feeling the Plancks, I'm like, dude, you're not going to feel the Plancks. You just, I mean, if you're psychic, something, you know, maybe somehow you got in there, but like, it's not the typical thing, oh, dude, these Plancks are in my way. They're not so obvious. In fact, you know, imagine a bubble the size of 40 trillion kilometer, right, diameter, this bubble, and you're putting grains of sands in it. How many would fit in there? That's inside a proton, right? So, you know, this is way below the typical experience you have. So, of course, when they renormalize the electromagnetic field, the Planck, you know, remember they cut off the electromagnetic field at the Planck distance? Okay, when they did that, then they were able to calculate how much energy there is in a centimeter cube of space, how much of the electromagnetic fluctuation of the little Plancks there is in a centimeter cube of space. Well, you know, we just saw how many grains of sand goes in between here and Alpha Centauri, so you can imagine that's inside a proton. Forget a centimeter cube of space, right? So in a centimeter cube of space, a lot of little Plancks go in. And because each little oscillator, of course, because of E equals mc squared, right? The energy is equal to this energy. You can transfer the energy of the little oscillator into a mass, right? You can express it in terms of 10 to the minus 5 grams. That's the mass of one little Planck oscillator hanging out down there in the very, very, very small, right? It's oscillating really fast because that's a lot of mass from one little teeny weeny bitty little Planck. Okay? So you calculate that and you end up with 10 to the 93 grams per centimeter cube. 10 with 92 zeros. So let me help you with that. You might have noticed in your bank account, when you add zeros, things improve rapidly. Right? It's, you know, exponential, so it's like 1 0, you have 4 zeros, it's okay. You have 5, it's better. You know, you got 6, it's like, wow, you know. You got, you know, 7, whatever. 93, though, is a lot of zeros. So how dense is this stuff that you call space, then? Well, if I took a centimeter cube of space and put all the stars in the universe in it, there's billions of stars in each galaxy. I take all the galaxies, there's billions of galaxies, I stick them all in a centimeter cube of space. Imagine how dense that would be. Okay? That would be 10 to the 55 grams per centimeter cube. I'd still be missing 39 zeros to make it to the vacuum density, to the amount of electromagnetic energy in a centimeter cube of this stuff we call nothing. We call space. So, in fact, matter might be a little space in the space, right? A little boundary that kind of pushes some of the Plancks into different density, right? The space may be denser than the matter, is what I'm telling you. Meaning that what we call matter or energy or mass may be just a little bit of energetic leak of the Planck field, which is otherwise smooth. So that over here, it's like organized, like the Plancks are like all kind of oscillating together nicely. And over here, they're more like, you know, hanging out.